Hey guys, this is test 29, game 1. This is the accountant with 7 bills game. It is a splitting game, which is kind of similar to an in-out game sometimes. Basically, the difference is that with a splitting game, both groups are actually present, rather than one group being in, the other group being out. Now, they tell us that on Tuesday, the accountant has to pay 7 bills by Thursday, but the day of Tuesday ends up actually being irrelevant, because the first rule of the game tells us that we have either 3 on Wednesday and 4 on Thursday, or vice versa. If 3 are on Wednesday, 4 are on Thursday. If 4 are on Wednesday, 3 of them are on Thursday. Don't worry about the bottom diagram here, we'll deal with that later. Now, they tell us that the 7 bills have to be paid. The bills themselves are actually our variables here. They're actually what we're going to be placing. I know that oftentimes with other types of games, when you have numbers, the numbers form the base of your diagram. That's not the case here. Here, the numbers are actually the variables themselves that we are placing, rather than letters like A, B, C, D, E, F, G, for example. So, the first rule of the game gives us these two top diagrams. If 3 were on Wednesday, 4 would be on Thursday. If 4 were on Wednesday, 3 would be on Thursday. They tell us that 1 and 5 cannot be paid on the same day. This means that these variables are split. We will have 1 Wednesday and 5 Thursday, or 5 Thursday and 1 Wednesday perhaps. So 2 different possibilities here regarding the placement of these variables. Same for the other diagram. One of the 1-5 pairing is on Wednesday. The other one of that pair will be on Thursday. The next rule tells us 2's on Thursday. That's easy enough to place. We just put 2 in the Thursday column. Next, 4 and 7 are on the same day. Now, on the diagram on the right, the Thursday column is full. As you see, there's only 1 slot left. We could not possibly fit both 4 and 7 on Thursday. Therefore, in this diagram on the right, 4 and 7 will both have to go on Wednesday for certain. On the diagram on the left, where we have 3 on Wednesday and 4 on Thursday, we have a bit more ambiguity. I mean, 4 and 7 could go in the Wednesday column. There's room for them there. Or 4 and 7 could go on the Thursday column. There's also room for them there. So that's why I'm going to make 2 different versions of the 3 slots on Wednesday and 4 slots on Thursday diagram. On the top diagram, I will put 4 and 7 both in the Wednesday column. And then in the bottom diagram, I will put them both in the Thursday column. So I'm going to put 4 and 7 in the Thursday column on this diagram, as well as filling in the other variables. 2 on Thursday, 1 and 5 split between Wednesday and Thursday, because of course those rules still apply. They tell us that if 6 is on Wednesday, 7 is on Thursday. So in the diagram on the top left, obviously 6 could not possibly be on Wednesday. We've already filled that up. So both 6 and 3 will have to go on Thursday, of course. In the bottom diagram, 3 and 6 will of course have to go on Wednesday. There is no room for them to go anywhere else. However, in the diagram on the top right, 6 on Wednesday would require 7 on Thursday. However, 7 is already on Wednesday. Therefore, it is impossible to have 6 be on Wednesday. 6 will have to go on Thursday, leaving 3 to go on Wednesday. And these are our 3 different main possibilities for the game. Every single valid scenario will fall within one of these 3 diagrams, and this is our setup for the game. Number 1, if exactly 4 bills are paid on Wednesday, what could those 4 bills be? Now, luckily for us, we have only 1 diagram out of the 3 in which we have 4 variables on Wednesday, right? The other 2 have 3 on Wednesday. Those are not relevant to this question. We know that there are only 2 possible layouts here. We could have 1, 3, 4, and 7 as our bills for Wednesday, or we could have 3, 4, 5, and 7. So 1, 3, 4, 7, or 3, 5, 4, 7. Choice D for number 1 lists 3, 4, 5, 7, and that is our answer. There is no choice with 1, 3, 4, 7. So D is our answer to number 1. Next, number 2, what's a complete and accurate list of bills, any one of which could be the bill paid on Wednesday? So if you look across your diagrams, of course, we always have bill number 2 on Thursday. So any choice containing 2 is automatically eliminated. That gets rid of both D and E because they list 2 as being on Wednesday, which of course is impossible. Now, if you look at the three diagrams here, you'll see that every single other variable, every single other bill appears on Wednesday at some point. We have number 1, we have number 3, we have number 4, we have number 5, we have number 6, we have number 7. So 1, 3, 4, 5, 6, 7, basically every bill other than 2 appears on Wednesday at some point. So choice C is our answer to number 2. Next, number 3, if 2 and 6 are paid on different days, if they are separated. So the top right diagram does not apply because it has 2 and 6 together. The top left diagram does not apply because it has 2 and 6 together. Only our bottom left diagram applies where we have 2 on Thursday and 6 on Wednesday. That's the only diagram that's relevant here. So what must be true within this particular diagram? 3 bills on Wednesday? Yes, of course, we have that right here. So A is our answer to number 3. Next, number 4, if bill 6 is paid on Wednesday, what else must also be paid on Wednesday? So obviously, once again, the top 2 diagrams have 6 on Thursday, not relevant. We're looking at the bottom left diagram here, where we have 6 on Wednesday. And in this diagram, of course, we also have to have 3 on Wednesday for certain, so B is our answer to number 4. While either of 1 or 5 could have been on Wednesday, either of those could have also been on Thursday, so those are coulds, not musts, and B is our answer to number 4. If bill 4 is paid on Thursday. So obviously top left diagram is not relevant because we have 4 on Wednesday there. Top right diagram is not relevant because we have 4 on Wednesday there. Only the bottom left diagram here has 4 on Thursday, so that's what's relevant for this question. What pairing of bills could also be paid on Thursday? Well, lots of things, right? I mean, we could have 1 and 2, we could have 1 and 4, 1 and 7, 2 and 5, 2 and 4, 2 and 7. Any of those would be good. Process of elimination is easier here. Could we have both 1 and 5? No, they are separated according to the second rule of the game. Only one of them appears on Thursday, so A is eliminated. B, 1 and 7. Yes, we could have 1 on Thursday, and then of course 7 is always on Thursday in this particular diagram, so B is our answer to 5. I'll go through the rest though. 3 and 5, no 3's on Wednesday, eliminated. 3 and 6, again 3's on Wednesday, so that is eliminated. And E, 6 and 7, no, while 7 is Thursday, 6 is Wednesday, that could not be a pairing of both of which are on Thursday, so B is our answer to number 5 if you didn't get it before. Next, number 6, what must be true? General question, we are looking at all 3 diagrams, all of them are relevant here. If 2 were on Thursday, would 3 have to be on Wednesday? Well, of course, 2 is always Thursday, right? That happens every single time. In that case, do we always have 3 Wednesday? No, of course not. In the top left diagram here, we have 3 on Thursday, not Wednesday, so A is eliminated. B, 4 Thursday, 1 Wednesday. Well, 4 Thursday only happens in the bottom left diagram here, and in that case, 1 could still go either way, so for that reason, B is not a must, it's only a could. C, 4 Thursday, 3 Wednesday. 4 Thursday does not occur on either of the top diagrams, only in the bottom one is 4 on Thursday, and in that case, yes, 3 must be on Wednesday. So C is our answer to number 6. I'll go through the rest though. If 6 Thursday, 3 Thursday, well, 6 is Thursday here, but 3 could be Wednesday in that case, so D is not a must. It's actually not even possible for this case. E, 6 Thursday, 4 Thursday. 6 is Thursday in both of the top diagrams, and in both of those 4 is on Wednesday, not Thursday. E is eliminated. C is our answer to number 6.